Welcome to the deep dive. Today, we're tackling a really interesting challenge in robotics.
Oh, yeah. What have we got?
It's about getting robots to, really see and navigate spaces like our homes or offices where things are always changing, moving around.
Ah, the dynamic environment problem. That's a big one.
Exactly. And our guide for this is a research paper. It's called Visual SLAM, based on semantic segmentation and geometric constraints for dynamic indoor environments. Quite a mouthful.
Yeah, typical academic title, but the topic's crucial.
Right. So our mission for you listening is to kind of unpack how this research tries to improve on existing robot navigation smarts, especially when dealing with, well, moving objects, moving people.
And to get the gist of the new ideas they're bringing to the table, because honestly, if robots are going to be truly helpful outside of very controlled factories, they need to handle this dynamism.
They can't just assume everything's frozen in place.
Not at all. This paper gets right into that core issue, making simultaneous localization and mapping SLAM work reliably when the world isn't static.
Okay, let's pause there. SLAM. Maybe a quick refresher.
Sure. So imagine you walk into a completely dark room you've never been in before.
Okay, pitch black.
You start feeling around, right, building a mental map of the furniture, the walls, while also trying to figure out where you are standing within that map you're building.
Got it. Map building and self-location at the same time.
Exactly. That's SLAM. Now, if instead of feeling around, the robot uses a camera to see the room, that's visual SLAM, via SLAM.
And that's fundamental tech for, like, robot vacuums, drones, even self-driving cars.
Absolutely. VSLAM algorithms, and a popular one is OrbiSLAM 2, which this paper looks at, work by spotting unique visual landmarks, feature points.
Like the corner of a table or a pattern on the wallpaper?
Precisely. By tracking how these feature points seem to move as the robot moves its camera, it estimates its own motion and builds that 3D map. But, and this is the key thing.
There's always a but.
Right. The big assumption in many systems, like OrbiSLAM 2, is that those landmarks, those feature points, stay still. The environment is static.
Which, in reality, it almost never is. People walking, chairs moving.
Exactly. That's where things get messy for traditional VSLAM.
So what happens? How does the movement mess things up?
Well, the system gets confused. It sees a feature point, say, on your moving cat, and thinks it's a fixed part of the room.
Oh, okay, so it misinterprets the movement.
Right. And that leads to errors in figuring out its own position and orientation, its pose. Plus, the map it builds gets cluttered with these temporary things, these moving objects, ghosts of movement almost.
So the robot might think it's drifted sideways because it tracked my leg walking past.
Sort of, yeah. Or the map ends up showing a faint outline of where your leg was, which isn't helpful for navigating later.
Makes sense. The paper digs into specific problems with OrbiSLAM 2 then.
It does. They pinpoint a couple of key weaknesses. First, how it finds those feature points in the first place. It tends to really focus on areas with lots of visual detail, rich texture, they call it.
Like a busy bookshelf.
Exactly. But it struggles in areas that are more plain, like a blank wall, weak texture areas.
So the feature points aren't spread out evenly. It's like the robot's only looking carefully at the interesting bits.
Pretty much. Which means its understanding of the whole scene can be skewed. You might miss important geometry because it's in a visually boring area. That's one problem. Uneven feature distribution.
Okay, what else?
The second big one, which we touched on, is those dynamic feature points, the ones on moving objects. They directly mess up the pose estimation, the robot's sense of where it is and how it's moving.
Right, because the calculations assume those points are fixed.
Correct. And finally, the maps themselves become less readable, less useful. They're cluttered with transient objects, making it hard for the robot to rely on the map for long-term navigation.
Is that a wall, or was that just Dave walking past earlier?
Okay, clear challenge. Dynamic stuff breaks traditional VSLAM. So let's get to the solutions. You said it's a multi-pronged approach.
Yeah, they tackle it from 3 main angles. First, improve how those feature points are found initially. Make the distribution better.
Get a more balanced view. Second, figure out a way to spot and ignore the feature points that are on moving things. Filter out the dynamic noise.
Okay.
And third, build a better kind of map, one that includes semantic information, knowing what objects are, not just where they are in 3D space.
A semantic map. All right, let's break those down. First one, improving the feature points. They mentioned ORB features. What are those, basically?
So ORB features are just a specific way of identifying these visual landmarks. They're designed to be fast to compute and relatively robust to changes in viewpoint or lighting. Think of them as distinctive visual fingerprints.
Well, they cluster, as you said. So how do they fix that? This homogenization algorithm.
Right. It's pretty clever. They use something called a quad tree. Imagine dividing the camera image into 4 equal squares.
Okay.
If a square has too many feature points crammed into it, they divide that square into 4 smaller ones, and they keep doing this subdivision until each little region has a more balanced number of points or gets small enough. Then, from each final region, they pick the strongest, most representative feature point.
Ah, so it forces a more even spread across the whole image, like making sure you look at every part of the room, not just the fancy painting.
Exactly. It prevents those clusters in high-texture areas and ensures better coverage.
And what about the blank walls, the low-texture spots? How do they find more features there?
For that, they use an adaptive threshold. So instead of having one fixed sensitivity level for detecting features everywhere,
They adjust it.
yeah, in areas where the image looks very uniform, very plain, they lower the threshold. They become more sensitive, essentially looking harder for even tiny variations in brightness that could signal a feature point.
So they're tuning the detection based on the local area.
Right. And they also use an image pyramid, basically looking at the image at different scales, like zooming in and out, which helps find features of different sizes, further boosting detection in those tricky uniform areas.
Does it work? Do they show improvement?
They did. They tested it on a standard data set, the Oxford data set, and they reported a 56.3% increase in the uniformity score. Basically, the points were much more evenly spread out.
That sounds significant.
It is. And they also found it improved the ability to correctly match points between different views, even with blur or lighting changes. So yeah, the improved extraction seems pretty robust.
Okay, step 1, better, more evenly distributed eyesight. Now, step 2, dealing with the moving targets, filtering out the dynamic points. How?
This involves combining 2 techniques: semantic segmentation and motion consistency.
Semantic segmentation. That sounds like understanding the meaning of what's in the image.
Pretty much. They use a deep learning network, specifically one called DPT, which uses transformers, kind of the tech behind things like ChatGPT, but for vision to classify pixels in the image.
So it labels things like, this is a person, this is a chair, this is the floor.
Exactly. It identifies potential dynamic objects like people, because people tend to move. The DPT network is quite good because it looks at the whole image context.
But you mentioned earlier, sometimes these networks aren't perfect. The segmentation might be a bit off.
That's true, which is why they don't rely only on that. They add a geometric check, the motion consistency detection.
Okay, how does that work?
This part looks at groups of nearby feature points, typically triangles of 3 points. It checks how the distances between these points change from one video frame to the next.
Ah, so if all 3 points are on a static object, like a table, the distances between them should stay roughly the same as the robot moves.
Precisely. The triangle formed by those points should move rigidly. But if one of those points is on, say, a person walking by, while the other 2 are on the static background,
The shape of that triangle will distort. The distances will change unpredictably.
exactly. The algorithm flags points involved in these distorting triangles as potentially dynamic because their motion isn't consistent with the surrounding static scene.
That's neat, using the geometry itself to spot inconsistencies.
And they add one more clue: depth information. They assume they have an RGBD camera, which gives distance measurements.
Right, tells you how far things are.
So, if a feature point belongs to an object moving towards or away from the robot, its depth value will likely change quite abruptly between frames compared to static points. That's another piece of evidence.
There's like a multi-layered filter. Is it likely a person's semantic? Is its motion inconsistent with static points nearby? Geometric? Is its distance changing rapidly? Depth?
You got it. Combining these helps create a much more robust way to identify and then filter out those troublesome dynamic feature points before they mess up the SLAM calculations.
And how effective was this filtering in their tests?
Very effective, especially in highly dynamic scenes. They used another standard benchmark, the TUM dataset, which has sequences with people walking around a lot.
High dynamic, yeah.
In those, they saw huge reductions in error. The paper mentions an average absolute trajectory error that's AEE reduction of 68.8%. And in the conclusion, they even quote numbers like 96% reduction in AEE for some high dynamic scenes. Massive improvement.
Wow. Almost eliminating the error caused by moving people.
Pretty much, yeah. Even in scenes with less movement, like people just sitting, they still saw benefits around 41% EE reduction there. Because even small movements can introduce noise. Figure 6 in the paper shows it nicely. You see all the feature points initially found on people, and then after filtering, those points are gone.
That's impressive. It really drives home how much impact dynamic objects have.
Okay.
Okay, so that's filtering. What about the third part, the semantic map?
Right. So instead of just having a map that's a cloud of 3D points showing the geometry.
I want a map that understands what those points represent.
Exactly. Wall, floor, chair, table. Each point in the 3D map gets a semantic label. This is way more useful for a robot. It doesn't just see an obstacle, it knows it's a chair it might be able to move, versus a wall it definitely can't.
How do they build this semantic map?
Well, they take the 3D points derived from the depth camera, get the color information too, and then they use the labels from that semantic segmentation network we talked about earlier.
The DPT network.
Right. That tells them if a point corresponds to a wall, floor, person, etc. And crucially, they filter out the points identified as dynamic before adding them to the long-term semantic map. So no ghosts of moving people cluttering the final map. Figure 4 has a good diagram of this workflow.
Makes sense. And they mentioned something about drawing keyframes to keep the map from getting too dense.
Yeah. Keyframes are like important snapshots the SLAM system uses. If you used every single keyframe to build a dense 3D map, you get loads of redundant data, making the map huge and slow to use.
Like taking 50 photos of the exact same thing.
Kinda. So they have a smarter way to select which keyframes actually contribute points to the final dense map, the drawing keyframes.
How to choose them.
2 main criteria. First, does the new keyframe see parts of the scene that previous drawing keyframes didn't see well? Does it add significant new geometric information? They call this common vision relationship detection.
So prioritize novelty.
Right. And second, they check how visually similar the new keyframe is to the existing drawing keyframes. They use a technique called bag of words with TF-IDF. Basically, it compares the visual vocabulary of the new image to the map's existing vocabulary.
If it looks too similar to what's already mapped.
It probably doesn't add much value, so they might skip using it as a drawing keyframe. TF-IDF helps weigh the importance of different visual features in this comparison.
So it's about finding a balance. Comprehensive coverage without excessive redundancy.
Exactly. And the result, which they show in Figure 10, is a semantic map that's much cleaner, less redundant, and clearly shows the structure of the environment with all the objects labeled, much better than just using all keyframes.
Any downsides noted there?
One potential issue they mention is if a dynamic object is always blocking the view of something static behind it. Since they filter out the dynamic object, the static thing behind it might never make it into the map. A sort of permanent blind spot caused by temporary occlusion.
Okay, interesting edge case. Now, crucially, did they just use data sets, or did they try this on a real robot?
They did. Real-world testing is super important. They used a turtlebot, a common research robot with a Kinect sensor, driving it around office and corridor environments.
With people moving around?
Yep, 1 to 3 people moving at normal speeds while the robot moved too.
And did the real-world results match the simulations?
Largely, yes.
Yeah.
Their improved feature point distribution worked well in the real office scenes, picking up more features on things like plain walls compared to the original IELTS SLAM 2. That's in Figure 12.
Good. And the dynamic filtering?
Also effective. Figure 13 shows it removing feature points on the moving people in the real environment. They did note, though, that it sometimes struggled with people far away or moving very slowly.
Why is that?
Likely limitations in the semantic segmentation accuracy at distance, or the motion consistency check isn't sensitive enough to very slow, subtle movements relative to the robot's own motion. Real-world noise is always harder.
Understandable. And the final maps, the semantic point clouds.
Figure 14 shows those. They look much clearer than what you get without the filtering, showing the office structure, furniture, walls, floor, all semantically labeled and without the trails of the moving people.
Okay, so summing up, this research seems to make some solid steps. Better initial feature detection,
More uniform, yeah.
a clever combo of semantic understanding and geometric checks to filter out moving objects.
Which significantly cuts down errors.
And finally, building these richer, cleaner semantic maps.
Exactly. The quantitative results, like that 56% uniformity boost and the big drops in trajectory error, are pretty compelling evidence.
And they're upfront about limitations, too.
Oh, yeah. They mention that relying on ORB features still makes them vulnerable to things like motion blur or drastic lighting changes. And the semantic segmentation network, while powerful, is computationally heavy and not perfectly accurate.
Which points towards future work.
Definitely. They suggest things like integrating deep learning more directly into the pose estimation part itself, not just for segmentation, and also working on lighter, faster segmentation models for real-time use on robots with less computing power.
Right. So for you listening, hopefully this deep dive gives you a good sense of how researchers are pushing robot perception forward. It's not just about geometry anymore. It's this blend of geometry and semantic understanding. Knowing what things are is becoming just as important as knowing where they are.
It really feels like a crucial step towards robots that can function more robustly and, well, intelligently in the messy, unpredictable environments we actually live and work in.
Which leads to a final thought to maybe chew on. As robots get better at seeing and reacting to dynamic worlds like ours, how does that change things?
Yeah. How does it change our interaction with them in our homes, workplaces, public spaces? What new things become possible? What new questions, maybe even ethical ones, pop up when robots can navigate among us so seamlessly?
This kind of research really opens the door to that future where robots aren't just tools in a controlled space, but maybe more like collaborators in our dynamic world.
A fascinating prospect, definitely.